Hey class, good afternoon. Mr. Bean here. This is for AP Physics, Unit 6, Rotational Motion. So this topic here, my video presentations will be in three parts, Part A, B, and C. Part A will get us into the kinematics of rotational motion. Part B will be talking about torque, and rotational equilibrium. And then part C will be rotational dynamics, which includes moments of inertia and angular momentum. All right, so here are some learning targets. So you should have your note taker out with you so you kind of read with me. Uh, so here are the learning targets. So in this presentation, you should learn how to convert angles to radians and so on. So radians to revolutions, back to degrees. Introduction to period and frequency again, working with angular frequency, and also using angular acceleration. Okay, so go ahead and go down here. Now, a lot of you guys might be in trig or have had trig or higher. So a lot of this, let you read this here. A lot of this should be review. Okay, and we'll come on down here. And one of the questions that might be asked for you to do is, can you convert 180 degrees into radians? Okay, and there's a formula here for you to do it. And just to make sure you guys are on board here, you guys go ahead and try um, number one and number two. Hit pause, go ahead and enter the solutions into Edpuzzle, and then I'll work them out after we take our pause. Okay, for the solutions, what I like to do is I like to say that like 360 degrees is equal to 2 pi radians, like this. And also I'll throw in there, it also equals one revolution too as well. So we might need that, but not yet. So anyways, so here we have what, 23 degrees. We're going to use the factor label method, and we'll go ahead and put down 360 degrees here. And up here, I'll go ahead and put down 2 pi radians, like so. And this here should equal 23 times 6.28 equals that, and divide by 360. So it should give us about roughly 0. We'll say 401. Okay, 0.401. Okay, and then in number two here is asking what is pi over 16 in degrees. All right, so this is assumed. So here's pi, and this is in radians initially. So we're going to put radians here, right? And we'll do the factor label method. So this is just 3.14. And what is it in degrees? So we know that there are, what was it, 2 pi radians in 360 degrees, like so. All right, so here you see the pi's cancel out, and so does the radians. So essentially, we just have 360 divided by 16, which should give us about 22.5. All right. Okay, in this next section, make sure you go ahead and read about period and frequency and understand the relationship and what's going on there. And here we have an example problem that you might want to look at to help you with some conversions and so on and so forth. And we'll come down here to number 3 here. You have a ball on a string and you're whipping around in a circle. If the radius of its circle is 1 meter and its period is 1 second, what's its speed? All right, so I'll go ahead and work this one out, and you guys will do number 4. So if a ball on a string, here it is, and it's going in a circle. Okay, so we have the radius here. Okay, and so what information do we have? So it says the radius of this circle is 1 meter. So we're going to put down 1 meter here, and its period t is equal to uh, 1 second. Okay, so 1 second, and is asking what's its speed. All right, so speed is 2 pi r divided by t, like so. Okay, divided by t. Okay, and so we'll go ahead and do this. Plug all the values in. V should equal about 6.28 meters per second. All right, we'll hit pause and you guys try number 4. All right, so number 4 here, uh, the uh, plugging everything in should be about 84 meters per second. It should be the solution on that one. Okay, so let's go ahead and down next section here, getting into angular velocity. So we'll go ahead and let you read about this here. And what we have here is the relationship for angular velocity is this omega here, this omega. Okay, so what this omega is asking here is asking about how fast does theta change with respect to time. With respect to time. So just, and then the next picture down here kind of shows more about it. So down here, here's omega, or excuse me, theta's changing, and there's some associated time with it. Okay, so the rate at which theta is changing while going in a circle, they use the symbol omega, which is like a W, and it's simply delta theta is over delta t. Now, what is this if we break it down? It means what's the initial angle, okay, or excuse me, the final angle minus the initial angle divided by t minus TO. Now, TO is usually 0, so it's just T normally, but this is what omega is. Okay, all right, so let's go and take a look at it again. So here's omega, and we'll just go ahead and put down here delta theta over T, like so. Okay, now what is this like, or what's similar to this? Okay, so remember velocity was change in position over time. So this will be the relationship or the analog to linear motion here. Okay, all right, so some other things in here. You may want to read this. This is an interesting read here. Make sure you get some background. Radian isn't a physical unit of measure. It's a ratio. Okay, so you want to make sure you understand what radian is. And to quite honestly, I haven't myself. I've never gotten a satisfactory answer, but that's what radian is here. And so we go over here and we can see, we can do some manipulation over here, and we can get this relationship right here for delta theta, or for delta theta. It's omega times delta t. Okay. All right. So here's a relationship here with some conversions you may want to look at, and make sure you get the answers here, radians per second. And here is number 5, 6, 7, and 8. I will do number 5 as an example, and you guys do 6, 7, and 8. Okay, so number 5, you have a toy plane on a string that goes around 3 complete circles in 9 seconds. What's this angular velocity? So it says 3 complete circles in 9 seconds. So let's write down what we have. So first of all, let's talk about what's delta theta. Okay, and also we have a delta t, or we have t given. Okay, the most straightforward one is start with t. It says here 9 seconds. So we're going to put down here 9 seconds. Okay, all right. So delta theta. So what is delta theta? So okay, normally, so if I do one circle will be 2 pi radians, right? That's for just one circle or one rotation. But we have here, it says 3 complete rotations. So we have to take this and we have to multiply it by 3 because it does 3 rotations. So this is, so 2 pi radians is one rotation, but we have 3 of them. So we have this relationship right here. So we know that omega is equal to what we have here, delta theta, right, over, we'll say delta t, okay? And so delta theta is going to be, we can say here 6 pi radians, okay, 6 pi radians divided by 9 seconds. Okay, so we'll go ahead and do this calculation here, and I should get about 0.7, we'll say here, radians per second. Okay, hit pause. Oh, hold on, not paying attention. Hold everything. This should be about 2.1 radians per second. Okay. All right. So you guys go ahead and try number 6, try number 7, and try number 8. And we'll go ahead and check your answers. All right. All right. So number 6 here should just be what? Just pi radians per second. Or if you want, you could say 3.14 radians per second. All right. Number 7, take a look at number 7 here. And a satellite is orbiting the Earth at 8.7 times 10 to the negative 4 radians per second. How long will it take to circle the entire world? Okay, we'll let you work on that one. So number 7, T should be roughly 7,200 seconds, which is roughly about 120 minutes. Okay, and number 8 should be about 3 seconds. 3 seconds. All right, so this next section here, go ahead and read about angular acceleration. Okay, so here's the analog case right here, or linear case, delta v over delta t. So here we have alpha will be our symbol for angular acceleration. And so it equals delta omega over delta t. So what that really means is that it's really going to be omega minus omega naught, or initial, divided by delta t. Okay. Okay, just like up here, acceleration was v minus vo over delta t. Okay. All right. So here's an example here of what we might do here. So look at this example and kind of see what's going on. And we'll come down here to number 9, 10, 11, and 12. So go ahead and look at these and try to solve them, and we'll check our answers after you work on them. So enter your answers in Edpuzzle. All right, so this next section here is talking about using our kinematic equations again. And now here the guy's using an S, but you could put an X in here if you wanted to. So what this equation here is essentially is X is equal to was it here XO, right, plus V VOT, right, plus 1/2 was it a t squared. So that's what he's essentially doing here. So what this equation is here, essentially, you could just say, delta theta is equal to omega initial angular speed times t, right, plus 1/2 alpha t squared. So we'll be using this relationship right here for the next problems here. So here's a guy did a problem here, but it's an extreme detail. We'll come down here, and I will go ahead and do number 13 here, and then you guys can do 14, 15, and 16. So number 13 says your model globe is spinning at 1 radians per second. So that's our initial angular speed here. Is going to be, we'll say here, 1 radian per second, 1 radian per second. Okay, and you give it a push. And if you accelerate it so this is going to be alpha. So alpha is going to be 5, right? Radians. Make sure we have our units too. 5 radians per second squared. Make sure we don't forget that. How many radians has it turned? So basically, what's delta theta? Okay, what's delta theta? How many radians has it turned in 5 seconds? So t is going to be 5 seconds, right? Okay, so we have our formula here that says delta theta, right, is equal to, right, omega t, like so, right, omega t, plus 1/2 alpha, was it t squared? Okay, all right, so if I plug in all the numbers here, delta theta should be about roughly 67.5 radians. Okay, all right. Now we should, now this is in radians. Now, if they want to go to degrees, right? If they want to go to degrees, what we have to do? Yes, I mean, for example, if we had to go to degrees, we'd have to know that there are 2 pi radians, right? And this would be 360 degrees. Okay. What if they wanted revolutions? Okay, revolutions. So if it was revolutions, we know that 1 revolution, right, would equal 360 degrees. So we can go from radians to degrees to revolutions. So make sure that we're familiar with this. All right, so you guys go ahead and do 14, 15, and 16. All right, hit pause. Oh, all right. So his next part here is suppose there's no time. So let's go ahead and come over here, and this is going to be no time given. Okay, no time given. Okay, there's no time. So this is what we would use if there was no time. We would have to v squared is equal to VO squared, right? Plus, was it 2a, right? 2a, and we had here usually delta x, right? Delta x. So over here, we're going to have is omega squared, going to equal initial omega squared, right? Plus 2 times alpha times delta theta. Okay, this is radians or rotations or revolutions here. All right, so look at this solution here and see what they did here and see what happened. And we have 17. So I'll go ahead and do number 17, and you guys do 18. Okay, so number 17, a helicopter's blades are speeding up. Okay, so that means it's accelerating in 1 second. Okay, so in 1 second, here, so let's write down information that we have. So in 1 second, they go from 60 radians per second to 80 radians per second. So that means omega was initially 60 radians per second to the final omega, which is 80, right, radians per second. Okay. Yet the angular acceleration alpha is 10 radians, right, per second squared. What's the total angle the blades have gone to? So what is delta theta? Okay. Now, what does that mean? Or what is delta theta? All right, so we look at our formula here. We have omega squared is equal to initial omega squared plus 2 alpha delta theta. So plugging in all the numbers, and we want to solve for delta theta. If I do that, delta theta should be, check my work here, make sure I did it right, should be about 140 radians. 140 radians. Okay. All right. So you try number 18, and that will conclude part A, or Unit 6, Part A.